All right, so as promised, we're going to finish up the notes on 13.3 on the curvature. So we've just established the good formula, which we established on the previous page, and then we also established a formula for curvature for a two-dimensional function, which we have showing here. So let's go ahead and apply that. We want to find the curvature of y equals sine of x. So let's first of all find a formula for the curvature, which we're going to need f prime of x, which of course is cosine. We're going to need f double prime of x, which is negative sine of x. So the curvature formula for something in two dimensions, and I think that on the previous page here, we questioned, where to go? Down at the bottom. We were questioning, why is it doing that? There we go. We were questioning this this top piece, and the formula actually does have an absolute value symbol up there. Now remember that this is it's a function in two dimensions, so really this is more so than anything else, it's going to be the absolute value. I will attempt to figure out why that is specifically and get back to you guys on that one. So this is going to be absolute value of negative sine of x, that's f double prime, over 1 plus f prime squared, which is cosine squared, to the 3/2 power. So there is your curvature formula. And if you think about it, here's the general graph of sine of x. That is not very good, but we're going to go with it. So right here at pi halves, we would expect the curvature to be pretty large. At pi fourths, maybe not so large. And then at pi, we would expect there to be very little curvature, because you're talking about, you know, that right there. Whereas opposed to at pi halves, we would expect the change of the tangent vector over unit of time to be pretty substantial. Big time curvature there. So let's check it and just make sure that you know, what we're seeing is what we should be. We check the curvature at pi. Plug pi in. We get negative sine of pi, which is 0, over, as long as the bottom doesn't give us 0, and it doesn't really matter. It's going to be, what is that, 1 plus 1, so 2 to the 3/2 power, which is 0. So we do get a curvature of 0 at pi, which makes sense because there's, in this case, there's no curvature. It literally straightens itself out. If you did the curvature at pi halves, if you plug that in, let's see, sine of pi halves is 1, negative 1, absolute value of that's still 1. And then plug pi halves into the denominator, so cosine of pi halves is 0, so that's just going to be 1 to the 3/2, which is 1. So at pi halves you have a curvature of 1, which is a pretty substantial curvature. It's actually the most that you can have, I believe. Maybe I'm wrong about that. And then we can do the curvature at pi fourths. Plug pi fourths into the numerator, you get root 2 over 2. Plugging pi fourths into the denominator, we get root 2 over 2, but we square that, and that's going to be 2 over 4. So that's what, 1/2, so 1 plus 1/2, or 3/2 to the 3/2 power, whatever that is. Get a decimal approximation on that as 0.3849 or 0.385. So not a huge curvature, but there is still some curvature there at pi fourths. All right, the last topics. the stuff that we didn't learn that you were supposed to have already known somehow without my teaching it to you. Sorry about that. So we're going to talk about three things. The unit tangent vector, which we've already done, the normal vector, the unit normal vector, and then this one, which is called the binormal unit vector. So the tangent vector, unit tangent vector, we've already done this one. So we won't really spend any time on this. This is just the unit tangent vector, which is defined as r prime of t over its magnitude. Okay, the normal tangent vector, unit normal tangent vector, unit normal. I keep saying tangent vector. It's just the unit normal vector. The unit normal vector is defined, I'm going to extend my page here real quick. The unit normal vector is defined to be the derivative of the unit tangent vector divided by the magnitude of the unit derivative of the unit tangent vector. So the question might be, well, why is that? So if you remember that we kind of talked about this up in the first page, recall that t of t dotted with t prime of t equals 0, which means that t of t and t prime of t are perpendicular to each other. Well, a normal vector is perpendicular to the tangent vector, so if we take t prime of t and we were to dot it with t of t, we would actually get a normal vector. So in other words, take this t of t, p prime of t, and dot it with t of t, you would get 0, which tells you that the t prime of t is perpendicular. I'm going to erase that. Is perpendicular to t of t. And all I'm doing by dividing by t, the magnitude of t prime of t, is making it a unit vector. I hope that made sense because it didn't sound like the way I was explaining it was all that good. But t of t and t of t and t prime of t, those two things are perpendicular to each other by the definition that I've gotten read down below. So that makes the t prime of t a normal vector, and by dividing by its magnitude, it becomes a unit normal vector. So if I were just to draw a real quick space curve of some kind of curve that's, you know, moving around in space, who knows exactly what it's doing. But if I were to find, excuse me, the tangent vector would be something like that. The normal vector would be perpendicular to that. So that would be n of t. This one in blue would be t of t. And then we have this last one, which is called the binormal unit vector. So let's go ahead and just do that one in black. Binormal unit vector. And that's b of t. So if you kind of break the words down here, it actually makes sense as to what it is. It says binormal, meaning it is normal to both of the tangent and the normal vector. So if you want to get a vector which is normal or perpendicular to both the tangent and the normal vector, this is not easy to draw. As a matter of fact, I can't really draw it. It's going to come like straight out of the page. So we'll just put it going into the page, I guess, and show that it's doing something like that. But ultimately, it is perpendicular here, and it is perpendicular there. Not easy to see that, but basically it's either coming straight out of the page or going straight into the page. If you want to find a vector which is perpendicular to both the tangent and the normal unit vectors, you cross them. So the binormal unit vector is the the cross product. T of t cross n of t. That by far is usually the most challenging one to do because you need the other two in order to do it. All right, we have one example of this that I will run through with you guys real quick. So we are supposed to, for the helix, find T of t, N of t, and B of t. And let's add that we want to also find all of those when t equals 0. So we're going to find all of them in general, but then we're also going to plug it in when t equals 0. So let's find the tangent vector first. Unit tangent vector is r prime of t divided by its magnitude. I'm making all kinds of mistakes. I'm trying to rush through this too fast. That's the problem. All right, so we need r prime of t. That'll be negative sine t cosine t 1. Okay, we're going to need the magnitude of that, which will be the square root of sine squared t plus cosine squared t plus 1 squared, which is 1. Sine squared plus cosine squared is 1, so all of that is root 2. So then to write the actual unit tangent vector, it is r prime of t, which is this vector, divided by its magnitude, which is root 2. So we can write that, instead of dividing each piece by root 2, we can write it as 1 over root 2 times negative sine t cosine t 1. And then if I want to find the unit tangent vector at time 0, I just plug 0 in for all my t's, and let's see, what are we going to get here? Sine of 0 is 0. Cosine of 0 is 1 times 1 over root 2 is 1 over root 2. And 1 is just 1. Sorry, 1 over root 2. If I could multiply, we would be good. There we go. All right, we need to be able to find the normal vector, the unit normal vector. The unit normal vector is defined to be the derivative of the unit tangent vector divided by its magnitude. So I need t prime of t. Well, we just found t of t right here, so now we need its derivative. So 1 over root 2 stays, it's just like a coefficient. Then we take the derivative of each piece. So the derivative of negative sine is negative cosine t. Derivative of cosine is negative sine t. Derivative of 1 is 0. I now need its magnitude. So the magnitude of the coefficient is just the coefficient times the square root of cosine squared t plus sine squared t plus 0. So the inside of that is just 1, so the magnitude is 1 over root 2. So the unit normal vector is going to be t prime of t divided by 1 over root 2. Well, the good thing is I've got a 1 over root 2 here and a 1 over root 2 there. That's just going to go away. So ultimately, what we're going to get for the unit normal vector is just negative cosine t, negative sine t, 0. And that's the unit normal vector. So let's go ahead and find the unit normal vector at 0. That's pretty easy. That's just going to be, was it -1, 0, 0. And now we'll do the binormal vector, which is the cross of n and t. So the binormal is the cross t of t and n of t. And technically, it doesn't make any difference if you do n of t cross t of t or t of t cross n of t. You would just get a normal vector in the other direction if you did it the other way. So the vector would be exactly in the opposite direction. One would be going into the page, the other would be coming out of the page. Either way, it's still a binormal. So if we want to do that, we're going to go ahead and take the cross product of t and n. So t of t, I do have to kind of distribute the 1 over root 2 through here. So we're going to get negative sine t over root 2 cosine t over root 2 1 over root 2. That's t of t. N of t, negative cosine t, negative sine t, 0. All right, so let's see what we get for a cross product here. If we eliminate the I row and column, we are going to get 0 minus sine t times 1 over root 2. So we should get sine t over root 2. The j row and column, we're going to get 0 minus cosine t times 1 over root 2. So that's cosine t over root 2, but we can't forget to change its sign, so that becomes negative. And then if I eliminate the k row and column, it looks like we're going to get sine squared t over root 2 plus cosine squared t over root 2, which means you add the sine squared and the cosine squared, you get 1 over root 2. And then obviously if you wanted to, you could factor out the 1 over root 2. So I guess I didn't have to multiply that in at the time, but it definitely needed to come in later. And that would be your binormal vector. And then we can figure out what the binormal vector is at 0 just by plugging 0 in. And we would get, is it 0, negative 1, 1. So 1 over root 2 times 0, negative 1, 1. And you could multiply the 1 over root 2 through if you wanted to. All right, so there you have it. There is the unit tangent vector, unit normal vector, and the unit binormal vectors. That should be plenty enough for you guys to go back now and fix the problems that we couldn't do from 13.3 day 1, and you should have everything that you need now to do 13.3 day 2.